Hi, it's Ryan. This is our second force example. This time we're dragging our favorite crate full of fruit, but we're going along a rough surface. All a rough surface implies is that there is a coefficient of friction between the surface of the ground and the surface of the crate, and that coefficient of friction was given as 0.3. We also begin pulling the rope at an angle this time, and they tell us the angle is 30 degrees above the horizontal. If we are now pulling the crate at a constant velocity, what is the tension in the rope? So we're looking to determine the tension in the rope. I started the picture for us. We can put our knowns and unknowns. We're given that mu sub k, which is between the surface of the crate and the ground, is 0.3. We know theta is 30 degrees. We know mass of our crate still 31 kilograms. And we know that A is what? Well, if we have a constant velocity, that means that the velocity is not changing, and A is a change in velocity, so of course A is 0. That's important and often overlooked by students when they read a problem like this. We know we're looking to find tension in the end. We might remind ourselves that tension is, of course, a force. So that's not a bad picture. Again, we're working with forces, and the way that we should always try to solve a problem with forces is to construct or draw an FBD. And we're going to do that of the crate again. So here's our crate. Let's put the forces that are acting on the crate. There's, of course, that tension force, T. There's a weight force. There's a normal force. But now there's a friction force. And what way will our kinetic friction force be pointed? Well, the crate's moving along. We could have noted in our picture that there's some velocity that it's moving that direction. And so that means the friction will be opposing the motion. And so our friction force will be pointed this way. So those are all the external forces acting on the crate. And honestly, if you were taking good notes, or if you look at that handout that I posted for you, this covers all the contact forces and the action at a distance force, all the possible forces we could really be working with, except the spring force. Well, there's no spring in this problem, so that makes sense. You can always look through those forces that we gave you on the handout or that I discussed in the previous videos to make sure you're not forgetting any. That doesn't mean you should always be using all the forces. That only means that that's your checklist to make sure you've tried to cover all your bases. Anyway, the next step would be to draw an acceleration vector, but there is none. A is 0. So now we need to choose a coordinate system. I could draw a coordinate system in any direction that I want, but it seems like drawing a regular XY coordinate system will keep most of my vectors only in one direction. It seems that if I do this, the only vector that is not pointed in either an X or a Y direction is the tension force, isn't it? So I can split the tension force into its horizontal and vertical components. I'm going to label it Ty and Tx, and I'm also going to show the angle that we were given in the problem. It might be a good habit to form as soon as you draw a right triangle here. We could show that sine of the angle is Ty over T, and cosine of the angle is Tx over T. That's just for this triangle in particular. Opposite is Ty, adjacent is Tx, and that's how we get these sine and cosine identities. And we're just going to keep those there in case we need a Tx or a Ty later. So that's a nice complete FBD. Next, we should sum the forces in the X direction and in the Y direction separately from each other. That's really why we spend the time to draw this nice FBD and to separate the x and the y directions in the first place, because we have to analyze them independent. So looking at the picture, let's look at the x direction forces first. It looks like there are two of them. We have a friction force and a tension component in the x direction. I always like to write my positive pointed directions first. So we have tension in the x direction minus the friction force equals, and will I write MA? Well, no, AX is 0. That's given in the problem, so it's equal to 0. Before moving on, I could label what these forces are. Tension in the x direction happens to be T cosine theta from our identity that we wrote here. And friction is always represented the same way. It's on that handout. And friction is always equal to mu sub k times the normal force. So I'm just going to go ahead and hold on to this. I don't know if I need it yet. It looks like I might. It has the tension involved. But I don't think I know the normal just yet, so I'm going to move on. Something you might note to yourself, a lot of students look at this and say, but the normal is equal to the weight. But it isn't, especially in this problem. And so you have to be very careful with that. That's why we have to make sure that you use all the direction of the forces before you start to make conclusions. So we're going to sum the forces in the y direction. It looks like we have 3 forces in the y direction. We have a normal force pointed upwards, so it's positive. A tension component in the y direction pointed upwards, so it's positive. And of course the weight of the crate pointed downward, so it's negative in our coordinate system. So I'm going to write those out. We have normal. The sum of the forces is just adding those 3 together, normal, plus tension in the y, plus weight, but weight's negative, so minus weight equals, and I normally would write MA, but A is 0, so we'll write equals 0. I'm going to go ahead and do what I did in the previous one. Normal stays the same. Tension in the y is T sine theta, according to this identity. And weight is always mg. Now I've got 2 equations and 2 unknowns, and it looks like what I need to solve for is the tension. But both of these equations also have a normal in there. So what I think I'm going to do is solve this equation for the normal force and then substitute it into this equation, and I can get my answer. So we have T cosine theta minus mu sub k n equals 0. I'm going to add this over, and then I'm going to divide by mu sub k. So I get T cosine theta divided by mu sub k equals n. Now I can substitute that in for this n. Actually, I think it would have been easier to just do it the other way, to substitute this expression into that, but it shouldn't matter, so I'm just going to keep going. So now we have T, so we're going down to here, T cosine theta over mu sub k, that's n, plus T sine theta minus mg equals 0. So this is a little ugly. What we need is T all by itself, so I'm going to multiply everything by mu sub k. That means mu sub k gets turned to 1 here, but it ends up in front of these 2 terms. And I'm going to add mg times mu sub k to the other side. So we'll get T cosine theta plus mu sub k T sine theta equals mu sub k mg. Now I'm going to factor my T out because it's a common variable. And finally, I can divide everything over and solve for tension. So tension is equal to mu sub k mg divided by cosine theta plus mu sub k sine theta. We can substitute our values, 0.3. Mu sub k is a unitless quantity. Mass was 31 kilograms. And g is 9.81 meters per second squared. Remember, we never put a negative sign in when we have mg like that. Then we'll have cosine 30 degrees plus 0.3 sine 30 degrees. And if you type all this into the calculator, you'll end up getting 89.8, I think. T equals 89.8 newtons. But t is a vector, and so we could say at 30 degrees above the horizontal. That is just at 30 degrees, so you really don't need to say above the horizontal. That's kind of redundant by definition of how we give our angles, so that's good. Another way you could have done this, and I'm not necessarily saying you should have in this case, but we could have figured out t sub x and t sub y independently, and then put those in there for this. But I think in this problem, the best and easiest answer is that, given that we were already given the direction of the vector. So there you go.